Welcome to another AP podcast. This is section 5.5. It's on Dalton's law of partial pressures. Now, last year we did a little bit of this, and the important thing to remember about Dalton's law of partial pressures is that each gas acts as if it were alone. So we don't worry about the pressure of any of the other gases. We worry about the pressure of each gas, and then when it's all said and done, if we want the total pressure of the container, we can go ahead and add them up, and that's what you see right here with the P total equal the pressures of all of the other gases. Now we know from our Pivner time that for each gas, P equals nRT over V. And what this does is this gives us a really important concept to think about when we're looking at another idea with pressure and moles and things like that. So imagine P total actually equals nRT over V plus nRT over T. And notice the 1, 2, and 3. That has to do with the fact that we're talking about gas 1 and gas 2 and so on, right? Well, if we know that that's what that equals, imagine the same container. Now, if we were in the same container, the gas constant would be the same, the temperature would be the same, and the volume would all be the same. So basically, we can kind of take those out of the equation, whatever the opposite of distribute is, and we basically get that the pressure total is really going to equal to the number of moles. And that's a really important concept. When dealing with gases, the pressure and the moles are directly related, and if you know one, you can figure out the other. And that becomes very important for the next thing, which is mole fraction. Mole fraction is very useful. Mole fraction is simply just the ratio of moles of a substance to the total number of moles. And it's going to be very useful for calculating some problems later on. But let's just look at some of the basics here. The symbol for mole fraction is chi. And in mole fraction, there are no units, for reasons I'll show you in just a second. So here's a formula. Now, mole fraction can either be the mole, and imagine this, let's say this is oxygen gas. We're going to find the amount of oxygen gas in air or something. So that's O2. We've got a 1 there and a 1 there. Imagine it's oxygen, and this would be maybe air. Okay, which I think we're going to do a problem like that in just a second. So the mole fraction is simply what part of oxygen is of the whole thing. Very much similar to calculating a percent, except we don't have the times 100. And so you can find it two ways. You could do mole fraction, which is moles over moles, or if you're not given moles, since previously we kind of showed that the pressure is directly related to the number of moles, you could also have the fact that the mole fraction is the pressure of one gas over the pressure of another gas. Super important concept because it's going to make our solving of some of these problems a lot easier if we just understand that basic thing. So let's get to a problem and see what it looks like. So the partial pressure of nitrogen air is 5.92 torr. The air pressure is 752 torr. And what is the mole fraction of nitrogen? So I'm just going to write the little formula here. So we've got chi, which is mole fraction. And that, in this case, is going to equal the pressure of nitrogen, N2, over the pressure of total. And that's really of air, right? So let's take the pressure of nitrogen, which happens to be 592 torr, and put that over the pressure of air, which is the total pressure, 752 torr. Oops. And you can see our units cancel, right? So therefore, mole fraction has no units. And so when I work that problem out, I get 0.787. Now that's the mole fraction. And that's going to be useful when we solve the next problem. Look at this next problem. What is the partial pressure of nitrogen if the container holding the air is compressed to 5.25 atmospheres? Okay, so just a little bit of little different there problem. Let me pick another color. So I've got mole fraction again, and we're dealing with pressures, so again it's going to be P of N over P of total, right? Now, we have the mole fraction of air and nitrogen from right here, okay? So let's stick that number in there. Let's go 0.787 equals, and we want to know what the new pressure of nitrogen would be if we compress the air. So that the mole fraction, pardon me, the pressure of air has been increased to 5.25 atms, and we're still looking, well, actually, we're looking for the pressure of nitrogen gas. Okay, so doing our awesome algebra, I'm going to times that by that. You guys know how to solve for x, right? And I get a pressure of nitrogen gas, in this case, equaling 4.13 atmospheres. Okay, now this has a unit, obviously, because we're left with atmospheres when we multiply those two numbers. So there you can see how mole fraction is useful in finding the partial pressure of another gas, which is exactly what we did there. And in this case, we did two problems. And like any problem that we do in this class, if you've got three variables, any one of them could be unknown and you'll have to solve for the other. So it's not too bad mathematically. So let's take this on to a little more real life situation. Imagine we have a container, and what happens often, let's say we have a container here, and it's full of water, okay, and I've got this Erlenmeyer flask. Here comes some amazing artwork, look out. Erlenmeyer flask, and I've got something going on, and I've got this tube, and we've got gas being generated here, and I've got a bottle right here full of water, and imagine as the bubbles go up, the water in here goes out, and so we collect this gas over water. Well, the important thing to remember is that water evaporates, and therefore, if it evaporates, it has a vapor pressure. Super important thing. So we could take the total pressure of this gas here. All right, we could take that total pressure, but it would be the pressure of the gas plus the water vapor. So in order to find the pressure of the gas, we have to just use Dalton's law of partial pressures, which equals P1 plus P2, and do that. And of course the math is real trivial, but it's something to be very aware of whenever you're given a problem where you're collecting water over, or collecting gas over water. You've got to deal with that water pressure. So let's go ahead and do a problem like that. So here we go. Look at this thing. Read it for a second. We've got some ammonium nitrate solid, and it breaks down. Gets heated up and makes some nitrogen gas and some water. And they can tell you what's going on. And then the key to this problem, of course, is this part right here. It says it's collected over water. All right, and so again, now we've got to worry about that vapor pressure. And notice they gave us the vapor pressure of water, real small number, which hopefully makes sense to you. Water's not going to evaporate at a real alarming rate, so the vapor pressure is going to be pretty small. So how would we do this problem? Well, it's a stoichiometry problem, isn't it? Because they tell us that we have 2.6 grams of ammonium nitrate. So what do we do with those grams? Well, let's find some moles. You want to? So let's do this. 2.6 grams of ammonium nitrate, and it turns out that 1 mole of it is 80.052 grams. And what that gives me is I have 0.0325 moles of ammonium nitrate. Okay. Now, so I know how many moles of this I have, but what we want to do is find the volume, if you look at the problem, the volume of N2O. So we've got to find this volume. So what's my next step? Well, to get from here to there, I've got to do a mole ratio, correct? Now let's see, is this balanced? 2 N's, 2 N's, 4 H's, 4 H's. Okay, this is a balanced equation. So my mole ratio is simply 1 mole over 1 mole, right? So what I get here is I get 0.325 moles of N2O. Now, what's our next step? Well, we've got to find the volume, right? So this sounds to me, since I'm given a temperature and a pressure, and I know moles, this sounds to me like a Pivnert problem, right? So volume equals nRT over P. So let's plug in the numbers we have and see if everything's going to work out. So I've got my moles, 0.325 moles. And I'm just going to write R. Bad teacher, I know, but we don't need to write that out. We've done it 100 times. And then the temperature, let's see, we've got a temperature of 22.0 degrees Celsius, right? So let's add that to 273, and we get a 275 K. And then our pressure, now here's where we've got to deal with something, okay? We've got a total pressure. See this right here? It says total pressure. Okay, so that since that's the total pressure, I've got to do a little finagling here and figure out exactly what the partial pressure is. So we've got a partial pressure of water to be 21 torr. Now, obviously we have an issue here, right? Atmospheres and torrs. We've got to change one into the other. So I'm going to go ahead and change my 21 torr into atmospheres, and there's 760 torr into 1 ATM, and that's going to give me 0.0276 ATMs, right? Well, I'm running out of room here. So I know, we get another color to try to keep track of things. I know that the P total, which happens to equal 0.928, equals the partial pressure of one gas, which in this case is 0.0276, plus the partial pressure of, in this case, N2O. All right? So doing our awesome algebra, I subtract that from that, and I get a pressure of 0.900 ATM. A lot of interesting little stuff to solve this problem. I like this problem. Okay, so I've got that. And when I do my math, 0.875 liters. Finally done. Woo! What a problem. So hopefully that all makes sense. Again, we'll go over this in class. And if you have any questions, let me know. See you next time.